Welcome back to Neal on Fire, where we talk with innovators, scientists, and leaders who are changing the way we understand, prevent, and respond to wildfires. Today, we're exploring a fascinating new frontier in fire monitoring, one that does not rely on cameras, satellites, sensors, or even a clear line of sight. We're talking with Madeline Hunt, a PhD student and researcher at Boise State University, who's using infrasound, which is low frequency sound, and Madeline's going to tell us more about that, to track fire behavior. Madeline, welcome to the podcast.
Thanks. Thank you for having me.
For listeners who may not be aware of infrasound, what exactly is it, and how do fires generate low frequency sound waves?
Yeah, so infrasound, like you said, very low frequency sound. And it turns out all sorts of natural sources on the earth make infrasound. So infrasound sensors are used at volcano observatories to monitor volcanoes because volcanoes, through all sorts of different mechanisms, make really low frequency sound. They're also used to monitor for avalanches. And you can use them for earthquakes, and then I use them for fire. Fires, we can start thinking about how fires make sound sort of intuitively. Like I'm sure you've heard a fire snapping as twigs and other vegetation releases water. And that's a very high frequency sound. Lower than that, if you have a big enough fire, you might hear roaring, like a nice roaring from a bonfire or something. That's caused by turbulence at the edges of the flames. And then even lower frequency than that, you get infrasound, which is caused by these big cycles of cold air coming in at the base of the cycle, heating up and rising. And these big cycles of gas flux are what create the infrasound that our sensors pick up on.
So, at what sound frequency does that happen?
Yeah, so the research that we've done so far shows that we get fire signal from about 4 to 8 hertz.
Which is well below where the human ear can pick up.
Yeah, the human ear, like we can hear about above 20 hertz. And so this is all well below what we can hear.
So tell me about this project. What inspired you to study infrasound as a tool for wildfire monitoring?
Yeah, well, infrasound is used, like I mentioned, to study all kinds of other natural phenomena. And my research group works closely with this local business that uses infrasound for avalanche detection. And so we got to thinking, well, what are some other important climate hazards that are happening that might need better monitoring systems? And fire, like wildfire, is a huge one. Fires are getting worse and worse. And so having better systems to monitor them or better tools we can give to fire crews is something that's really important.
So having said that, what gap do you think this fills in the wildfire monitoring landscape? Because we've got cameras, we've got satellite, we've got sensors, we have a lot of things in that wildfire detection ecosystem. Where does infrasound fit in?
Yeah, so infrasound, like you mentioned at the beginning, you don't need a visible line of sight because infrasound, very low frequency sound waves, because they're so low frequency, they can travel through the atmosphere for kilometers without attenuating, so without decreasing your signal strength. So we can set up our infrasound sensors very far away from the fire without putting our sensors or people in danger by being too close to the fire. And then also, infrasound isn't affected by smoke plumes for tree canopies. So our sensors can be put in any scenario and can detect a fire where a satellite camera might miss it because it's covered with green tree canopy above.
So your research summary highlights that infrasound can continuously record the entire duration of a fire. What changes in fire behavior show up in those signals from, say, the beginning to the end or in the middle? How do you determine kind of where the fire is in its life cycle?
Yeah, that's a really good question. And that's something I'm actively looking at because we think we might be able to tell the difference between like smoldering and active flaming combustion. And so those two things make different signals because the gas flux you're getting in those two scenarios is different. So we think that we can use infrasound to detect as the fire dies down over time. And someone else, one of the advisors in my research group, did some research recently where we were able to see a big pile burn, like a big bonfire. As it decreased in size, we saw the frequency decrease over time as the burn got smaller and smaller. So we're hoping we can see those effects in larger scenarios like wildfires or larger prescribed burns.
So I know what a camera looks like. I know what a sensor looks like. I got all those frames of reference, but I have no idea what an infrasound sensor looks like and how it operates. And we'll add an image here into the video, but give us a sense of kind of how this sensor operates.
Yeah, so our infrasound sensors, they were actually designed by my PhD advisor in our lab. I think we have over 100 of them that we make in our lab, but They're about, I don't know, 5 inches by 3 inches, the size you could fit in a lunchbox. And they're a plastic box. And on the outside of this box, there's a little nozzle that lets air in. And so, what the sensor is actually recording is pressure fluctuations. So, like sound waves, like me talking right now, is creating pressure changes in the air. And that's what our infrasound sensors are measuring, is that small changes in pressure from the base atmospheric pressure.
So I know some sensors operate wirelessly out there using protocols like LoRaWAN. How does an infrasound sensor connect? Does it connect into some kind of a central collection device, or take us through what that looks like?
So all of our sensors that we use are autonomous. You have your little lunchbox sized box. All you have to do is press the on button, set it on the ground, and walk away. And sometimes we will put a wind screen on top of it because wind noise is particularly bad for infrasound and can block the signals that we're looking for. But really, it's just press a button, put it on the ground, and walk away. And for us as researchers, this is fine. We go back. Data is stored on an SD card. So we go back after the fire, collect the sensors, and look at the data afterwards. But there are plenty of other systems that use infrasound that can transmit data in real time. Just as researchers, we don't need to worry about setting that up for our purposes.
Right. So how long does it take to deploy a set of these sensors? And are they kind of deployed depending on the topography, or are they in a certain pattern? How do you normally do that?
Yeah, that's a really great question. And another thing that I'm looking at specifically for my PhD dissertation. So, our infrasound sensors, to answer your question about time, really easy to deploy. And that's why we think this could really benefit the fire and land management community, is because it is as simple as you take it out, you press a button, and you walk away. And it just records the entire duration of the fire. And so that would be really beneficial for fire crews, land managers, because they could just put these sensors out, get the data, and like listen to what the fire is happening, and it could give them an early warning detection system. As for the patterns and the places we look for when we're deploying these, we tend to put our infrasound sensors underneath trees or in the middle of bushes because, like I mentioned, wind noise is really bad. It can interfere with the
Mhm.
signal. But putting a sensor underneath a bush, the bush blocks out all of those higher frequency noise from the wind, but we still get that low frequency infrasound signal that gets transmitted through the bushes or through the trees. And then the thing that I'm looking at specifically for my PhD is the configuration, the best configuration to put these sensors out in. So, one question I'm actively studying is how many sensors is enough that gives you good quality data that can detect a fire while also minimizing the amount of time and the cost to deploy these sensors. So, trying to find that right balance that fire crews could go out, put these out, and still get high quality data without spending a lot of time putting them out.
You were talking about the placement and how you put them under bushes to eliminate some of the extraneous sounds from coming in. Do you use some kind of an AI system to be able to look at what the accurate sound signature is and remove some of those extraneous sounds from consideration?
That's a great question. I know there are other infrasound researchers that do a lot of machine learning work to help detect what is signal and what is noise. My group does not, because for the most part, it's different frequency bands that you're looking at. Trained researchers can tell what is noise and what is fire, and noise tends to be higher frequencies than our fire signals, so we can just get rid of all of the data that's at those higher frequencies and focus on the lower frequencies.
So, with your planned development for prescribed burns, I understand that you're using 5 arrays with 20 sensors each placed around the perimeter of the prescribed burn. How did you design that setup?
Yeah. So when we are setting out our infrasound sensors, one thing that, like the main thing that infrasound data gives you is the direction to your signal source. So the direction that the fire is. And you can think about that like with our ears, we have directional hearing. So if someone is talking to your right ear hears the sound before your left ear hears the sound. And you can tell that someone is talking to your right. The same thing is true with our infrasound sensors. When we have two or more, we can use the timing of when a sound hits each of our sensors sequentially so we can tell which direction that sound is coming from. And if we have multiple arrays or multiple groups of sensors, we can triangulate and use those directions to triangulate on a map where that fire signal is coming from. So, this most recent prescribed burn we went out and deployed, it actually ended up being 4 arrays because of timing constraints. But we have 4 arrays around the perimeter of the fire. So, when I'm looking at the data, I can take the direction from each of those 4 arrays, cross those lines on a map, and pinpoint exactly where that fire signal is coming from.
You've talked about kind of more of the audible sound signature of branches crackling or the roar or what have you. Do you see some value in capturing that and maybe combining it with infrasound to be able to come up with a more accurate determination of wildfire spread?
Yeah, I think that's a great question. Our sensors currently don't have that capability. Our sensors can record up to 50 hertz. So that is barely in the audible range, but it's not at the level that you hear those snapping and different vegetation effects. But I do know there are some researchers that we work with that study audible sound from different vegetation in the lab. So they're burning different types of trees and pine needles in a lab and then recording the audible sound to tell the differences in it.
Your
But yeah,
key
I do think that would
research
be valuable. Sorry.
No worries at all. Your key research question is about balancing sensor count with data quality. How will you determine that point where additional sensors no longer provide meaningful improvements?
Yeah. So, what I'm going to do with the different arrays that we deployed, one of them we deployed in a grid pattern. So, it's multiple sensors in a grid. So, I can slowly remove sensors from this grid and get different array shapes, like subarray shapes within. So, maybe I have four sensors at the corners or four sensors really small in the middle. And I'm going to compare how well those sensors are tracking the fire, how well each of those subarrays is tracking to each other.
I understand that you record noise days before the burn. What does the baseline sound environment typically look like, and why is that important to the overall assessment?
Yeah, that's a really great question. It sometimes depends on the area that you are. So, one thing we'll notice is that at nighttime, sounds are generally easier to hear because the wind dies down and it's a lot easier to hear signals from different sources. One thing we have to be aware of, though, is we're not just picking up the fire signal that we're interested in, we're picking up all kinds of signals. So, we get anthropogenic noise from cities. That's one thing we have to look out for, depending on how close this wildfire, this prescribed burn is to a major highway or a city. We can pick up on that noise. And we're generally able to tell what is road noise or what is city noise based on the location and based on the time of day we're hearing it. So anthropogenic noise would be louder during the day as more people are active during the day. One thing I'm looking out for in these data sets is also waterfall noise. Waterfalls create a lot of infrasound. And if we get a consistent source of infrasound from a consistent direction, that's probably a good sign that we have a waterfall in that direction.
So, what would you say is kind of the number one environmental noise challenge that you have that if you could just eliminate that, it might make your work that much easier?
Yeah, so I have two big ones. One is wind, which I've talked about, and a second one is helicopters. So, wind, like I said, higher frequency, but we can sort of mitigate that with our placement of our sensors. And if we use a wind screen to cover it, that can also help block that wind noise. Helicopters are also really troublesome. You might get helicopters or aircraft if you're monitoring an active wildfire because they could also be flying overhead collecting data or aircraft dumping water. And those signals are pretty problematic. Helicopters specifically um, make sound at a rate that's proportional to how fast their blades are spinning. So if you're looking at your data and you see a really clear signal at, I think, 24 to 32 hertz, depending on the model of helicopter. That's a really good sign. And if you see that frequency changing, that's actually the Doppler effect in action. So as the helicopter flies away or flies towards the site, you can see the frequency of that helicopter slowly changing in your data. But yes, those signals are very annoying. Luckily, fire signals are way lower frequency than that. So what I've done so far is just ignore anything that's higher than about 10 hertz.
Okay. Well, I'll tell you what, we'll see what we can do to get rid of the wind and helicopters for you. Take care of that for you.
Great,
So,
thanks.
you mentioned previous research showing that even small burns with wet vegetation produce detectable infrasound. What surprised you the most about those results?
Yeah, so this is a prescribed burn that we looked at in Idaho. And it was really frustrating, like being there and waiting, like being a researcher waiting for this to burn because the burn kept being delayed because it was wet weather. And then when they finally did burn it, it was really patchy burning. So there were not, yeah, it wasn't like a big, beautiful fire that we wanted to see, which it achieved the land manager objectives. So we were grateful to let them collect data there. But one thing that really surprised me about that was that we were still even able to capture fire signal. So there is this one period of time that I focused on specifically where the fire sort of shot up this hillside really fast over a period of about 45 minutes. And our infrasound sensors were able to track that from the bottom of the hill slope all the way up to the top of the slope, track that fire progression. And so I was surprised that we even got usable signal in this data set because it was not a large fire at all. It was small and grassy, but we got really good data out of it despite that.
Hmm. Does that say that terrain might be working in your favor if you were catching that going up a hillside? Is there something about infrasound detection that might be a benefit in those kinds of environments?
Yeah, so terrain is a huge factor, and it's one that we are actively studying. So, infrasound signals, like I mentioned, can travel really far distances, kilometers, hundreds of kilometers away, depending on the atmospheric conditions. So, you can get infrasound refracted up in the troposphere, and it can travel really far and then get refracted back down towards the Earth. And so that's how it can travel these far distances. So if there were, for instance, a hill or a mountain in the way, you could still get infrasound because it's traveling up and around and over that topography. But that also depends on where the wind is traveling and what the other atmospheric conditions are, because sometimes they're not favorable to move infrasound over topography and that signal might be blocked. So that is a really good question. That's something we're looking into.
So, if the results meet with your expectations, who do you think would be the best early adopters? Would it be prescribed burn teams, land managers, forest agencies, firefighters? I mean, who do you see as looking at this technology and saying, wow, we got to do that?
Yeah, I mean, eventually I hope it's all of those people, but I think specifically prescribed burns might be a good place to start because one of the major benefits of infrasound over other technologies is that it could potentially catch reignitions really fast. I know that there was a big wildfire in New Mexico a few years ago, 2022 maybe or 2023, and that giant wildfire was caused by a reignition from a prescribed burn. So if you have infrasound sensors out, they could let you know and warn you, hey, we're detecting fire signal, even though you thought this fire was out. And that could get fire crews on the scene, put that out before it escalates into something worse.
So, in a real time fire situation, how quickly could this technology be deployed and how quickly could it be moved if it needs to go to a different location?
Yeah. So it depends on the area that you're going to. This summer, we put out sensors at the Immigrant Wildfire in Oregon. It was a really big fire, I think 33,000 acres. But basically, I heard about this wildfire. I was tracking on IncineWeb, the app. I love that app, but I was tracking when the fire started and I noticed that it was growing in size and I was able to get out there, I think 4 days after the fire had initially started. And the delay in that was just due to me being a PhD student, having to finish some work and packing my car with all of the sensors and then the drive it took to get from Idaho to Oregon. So it was a very rapid deployment. And we were able to put out the sensors and still capture a huge amount of the fire growth because it was still growing when we put out our sensors and we were able to capture a lot of the growth before it stabled off and they were able to manage it.
So, with that in mind, if you put out sensors and it detected the fire moving in that direction, obviously they're not going to survive the fire. So, you'd either have to pick them up at a certain point and move them further out, or they would be burned up in the fire. How do you see that working?
Yeah. So, one great thing about our sensors, I hate to say it, but they're cheap. They're relatively cheap. So if they get destroyed, I would be sad. Our lab would be devastated, but they are relatively cheap. So it wouldn't be like you're losing hundreds of thousands of dollars on these sensors. And another benefit of infrasound is that you can deploy them far away. So hopefully we put them far enough away that you're never in a situation where the fire is encroaching on them because you've deployed them far enough away that the fire hopefully will never make it that far.
Let's talk about that scenario where you were chasing the fire in Oregon. So, how many sensors did you put out and how far away from the active fire line were they?
Yeah, so I put out 3 arrays of 13 sensors each, so 39 sensors total. And I put them out. When I was monitoring the fire as it started and like reading the reports that they were putting out daily, I noticed that they had a really solid um, fire line to the north of the fire. And so I thought and the fire seemed to be spreading towards the south. So I thought I'm going to put my sensors to the north of the fire because it seems they have that line really well contained. So that, first of all, was a big, I think, very helpful to me. So I drove on the roads. I was looking for a mostly flat place to put my sensors and also being aware of, I didn't want to get in the way of the people doing the actual fire suppression work, the actual important work. So that was also controlling where I wanted to put my sensors. And they ended up being, I think the closest array is about 2 kilometers and the farthest array is 6 or 7 kilometers. And I have looked at this data and I can hear infrasound at all of those arrays. So even the array that's 6 to 7 kilometers away, it's hearing really nice fire sound.
Wow. So this is the life of a PhD fire researcher. You're tracking fires on the web, and when a good one pops up that's within a reasonable driving distance, grab the gear, throw it in the car,
Yep,
head over there. That's
pretty
great.
much.
Yeah.
I was waiting all summer for this too. I had some grant money to go out and take these sensors. And so I was basically every day checking the app, seeing when a fire was going to start, if it looked like it was close enough and going to be big enough.
So you actually get excited when there's a wildfire.
I know. I
Yeah,
know. It's terrible,
that's okay.
but at least we can get some good of it.
Yeah. So we've talked about prescribed burns. We've talked about the larger fires like in Oregon. Where do you see the best use case, or are there multiple use cases for infrasound for wildfire detection?
Yeah, I mean, I think there are multiple use cases. I think infrasound has shown potential in all of these scenarios. Prescribed burns, setting them out beforehand, or maybe you have an array close, like nearby a city, so you can monitor if there's any wildfires that start encroaching on a major population area. I think infrasound really has benefits in all of these scenarios because they are cheap, really easy to set up, and they monitor continuously.
So infrasound is at the infancy. Obviously, it's in the academic realm. You're having fun with it. You're learning lots of new things. But if everything goes right, where do you see this technology being in terms of wildfire monitoring in, say, 5 years?
I mean, so infrasound is used at like volcano observatories, and it's infrasound is also used with the nuclear monitoring treaty. There are infrasound arrays all over the world listening for people who might be testing nukes when they aren't supposed to be. So I see infrasound for fire monitoring something similar. We get big networks set up across the world or across the US that can just sit and listen and monitor for infrasound. Or these are just another tool in the pocket of land managers or fire crews that they can go out, put out, and just leave it there and wait for the data.
If I were to ask 10 people in wildfire if they knew what infrasound wildfire detection was, it's pretty likely that 9 or even 10 out of 10 would say they have no idea. So,
Yeah.
what's the one thing that you think is important that wildfire practitioners understand about infrasound with wildfire detection?
Yeah, I think the most important thing is that infrasound really fits in a niche that other technologies don't. It's not like data from aircraft where you can only do sweeps over the fire. Sometimes it is continuously monitoring. It can see around topography depending on what atmospheric conditions are. It could see through smoke plumes or hear through smoke plumes, and it can hear through tree canopies. So I think infrasound is this really valuable tool and gives really valuable data that fits in where all of these other technologies that we already have kind of have a blank space.
Do you ever see it being applied at more of a residential or a community level where someone might say, hey, I back up to the WUI. We've got a big wildfire problem here. I'm going to set out an array of 20 sensors and get that data back. I know it's not near that at this point, but would that technology work in that kind of environment?
I don't see why not. I think that could be totally a potential thing that people could do.
So this is super interesting. Now I want to go back and learn about how infrasound is used for volcanoes and earthquakes and all
Yeah.
that. But for people who are following this podcast, where can they learn more about your research on the project?
Oh, this is a good question. So I am currently writing a paper. All of the papers that I'll write and all of the code that I'll write for my PhD will be open sourced and accessible. Yeah.
There is some information on the Boise State University infrasound page, right?
Yes.
And
Yes.
I can provide that link so people can go there because there's some information, some research, and that would be a good way to follow what you're working on.
Yeah, absolutely.
We've talked quite a bit about infrasound here today. What's the one thing I haven't asked you that you think's important for people to know about this?
Let me check my notes real fast because I wrote down some
Wow,
notes.
maybe I covered it all.
I think you may have covered it all, honestly. I think some important things are infrasound is like a proven technology for all of these other forms of natural hazards. And the work that we're doing with fire is exciting and new and really has a lot of potential to really help a lot of people.
Madeline, thanks for joining us today on Neal on Fire. This research is a powerful example of how innovation can come from unexpected places, even from the lowest frequencies of sound. As we continue to search for better tools to understand and manage fire, breakthroughs like this will help move the entire field forward. If you enjoyed this conversation, make sure you follow the show, share it with someone working in wildfire, and also check out links to today's guests and their Infrasound wildfire research. Thanks for joining us today as we explore the cutting edge of wildfire innovation. Catch you on the next episode of Neal on Fire.